Okay, we're starting today our last unit, which is in chapter 12, and it's on three-dimensional solids. So a solid that with all flat surfaces that encloses a single region of space is called a polyhedron. I almost spelled that wrong. Oh, and of course now my pen's going to start having a delayed reaction, so I'll just fix that for you. It's P-O-L-Y H-E. You can call it polyhedra or polyhedron. Polyhedra is plural for polyhedron. Each flat surface or face is a polygon. The line segments where the faces intersect are called edges. The point where three or more edges meet is called a vertex or a vertex. Plural is vertices. Polyhedrons can be classified as prisms or pyramids. A prism has two congruent faces called bases, and they are connected by parallelogram faces. Now, mostly it's usually rectangles or triangles that are the faces, or any other shape could be the base. Oh, okay, a pyramid has a polygonal base and three or more triangular faces. So in these, the faces are triangles, and they meet at a common vertex. Polyhedrons or polyhedra are named by the shape of their bases. Now, the bases are not always what they're sitting on, so don't assume that. Other solids there's some other types of solids that are not pyramids or prisms, such as cylinders, such as a cylinder. I guess I shouldn't have that plural. That sounds weird. Other solids are a cylinder, which has parallel circular bases connected by a curved surface. So this is a cylinder, and this surface that is connecting those bases, the top and the bottom, that is a curved surface. It's actually a rectangle. A cone, which has a circular base connected by a curved surface to a single vertex. There's an example of a cone. Or a sphere. Okay, so note that these are not polyhedrons or polyhedra. All of these are. So the reason that this first one, so you understand how they're naming them, this one has a pentagon base, and it has two of those. That's why this is called a pentagonal prism. Okay? The way the next one's named, and since it's meeting at a point and its sides or faces are triangles, its base is the square. So that's how that one's named. The third one is a pentagonal pyramid. So it's got a pentagon for its base, and it is sitting on that. But notice the first one, this one's not sitting on the pentagon. Okay, it was sitting on the rectangle. The faces are rectangles. The faces of the pentagonal pyramid are triangles. And then there's a rectangular prism here. I don't know that these are squares, so we call this by its base right here, rectangular prism. The cylinder is a cylinder because it has two circular bases. The cone is a cone because it has a circular base and meets at a point. And then a sphere, well, that's just like a ball. It has its own special name. So on the next example, and this is in the ISN, determine whether each solid is a polyhedron. Then identify the solid. If it is a polyhedron, name the faces, edges, and vertices. The figure is what does that base look like it is? Yes, it does. It looks like a square, all right? So this is what we're looking at. and it's pointy, meeting at a point, and its faces are triangles. So this thing is a square pyramid. The base is a square ABCD, and the four faces are triangle ABE. That would be this front one. BCE, which would be this right side. The very back, CDE, is that triangle on the back. And then the triangle on the leftmost side, ABE. They all meet at vertex E. The edges are all of the segments that you see. So on the bottom, AB is one, BC is another, CD, and then DA or AD. Those are all the segments on the bottom. Those are all edges of the base. The edges on of the triangles would be AE. They didn't give us enough space for that. I need to make that line longer. AE, EB, EC, and this doesn't matter what order you write the letters, of course, because they're segments, or ED. Okay, so those are all of the edges of that figure. The vertices are simply all of the points where those edges meet. So that's just going to be A, B, C, D, and E. This next one is a cylinder because it has two circular bases. The two bases are the circle with center O, and you write it with that notation we've used before. You make a little circle symbol with a dot, and you're indicating that, bless you, that point O is its center. And the bottom one is the circle with center P. The solid has a curved surface, so it is not a polyhedron. It has two congruent circular bases, so it's a cylinder. Now, if I were to open that cylinder up, if you thought of it like you have one of those paper towel holders in your house, maybe that sits on the counter. If they sit on the counter, they're vertical. If your mom has them on the wall or, attached to the wall, they go like that. If you unroll that, what's the paper towel look like when you open it up? Well, no, it doesn't actually. When you pull one off, you get, yeah, rectangles. They're just rectangles, right? They go around there. But surprising how big they are. This one doesn't even, would fit pretty much around a roll of paper. It's about 2 sheets. That's what it looks like when you unroll the outside. So manufacturers need to know about how far it is all the way around. We're not going to be doing the surface area, but if you pulled that thing apart, you'd have a circle. If you were like take a can and rip it apart, you'd have a circle and a big rectangle. And the rectangle is actually quite a bit bigger than you think it would be. On this one, if I pulled that thing apart, I'd have a square and 4 triangles. Okay, and they could be opened up kind of like a flower. You don't have to draw this, but if you were to open this up, it's called a net. A net of that would look like this. Just let all these petals fall down. Can you visualize that a little bit? The net of this, you don't have to draw this, would be a rectangle, and then it'd have a circle and a circle. Okay. This figure, now, we often name this one incorrectly. Well, it does kind of look like a tent. I hear you. You want to call it a rectangular pyramid, but it's not. I'm hinting right now. Nathan, do you really think the bottom looks like a square? No, they are not. Squares are rectangles. Rectangles aren't necessarily squares. It is a triangular prism. It is a prism because it has two bases. Now, these are your bases. The bases are the triangles. Triangle ABC is one of the bases, and triangle DFE is the other base. Okay, why is this a triangular prism? Well, it's because you're supposed to name a prism by it's named by its bases. The bases are the shape that defines what it looks like. Now, if it was a square prism, then these would have to be squares. Okay, so and then it looked like a box. This one doesn't look like a box. It looks like a box, though, with bases that are triangles. Okay, so that's why this is a triangular prism. You look at the unusual shape to decide what it is, right? The faces are rectangles. So there is a face that's a rectangle, and it's going to be the rectangle. You can just name it CBEF. They're missing a blank. Why do I say that? I see 2 blanks. How many faces is that going to have? You got one on the bottom, ABFD. Don't we have another one? Yeah, what's about the back? Isn't that a face also? So ACED. You can name that many ways. You just need to go around in a consecutive order from consecutive vertices. Now, the vertices are all those little points. So AB, we got A, B, C, D, E, and F. And I'm not going to write down all the edges, but let's count them. There are, 3 edges on the left side of where that triangle is, 3 on the right, and then in between, so far we have 3 plus 3 would be 6 of them, and then 7, 8, 9. So there are 9 edges. These are 3 edges over here, 3 edges there, and then at the 3 going around. Okay, you're going to need, I think I have it set up where you just flip your page there over. Okay, continued. A cross-section is the intersection of a solid and a plane. You can think of a cross-section as a very thin slice of a solid. So we're going to discuss what those look like. There are several interesting shapes that are cross-sections of a cone. Determine the shape resulting from each cross-section of a cone. Now, if you were going to have to do this, you're going to have to know that if you slice a cone horizontally, as you move down, you're going to get a little circle, another circle, a bigger circle, and you keep getting circles that are a little bit bigger and bigger. So when you do a horizontal to the base slice with a plane, you're going to get a circle. If you go this way on a cone, now I went and got shapes out today. We're talking about this cone right here. Sometimes it's hard for you to see it on a 2D surface. So get it there. If I went horizontally to the base, every time I chop into there, I'm going to get a bigger and bigger circle. All of these going up to the tip would be just circles that are getting from small to large going this way. Okay. Now, if I cut it going this way, straight through the tip, you see how I'm going to get a triangle? Okay. And now, if I cut it this way, going like that way, I'm going to get an oval. Okay. It's not going to be fully round. Okay. It's going to be an oval if I go slanted like that. So that's what they're depicting on C. So I just did a demonstration to the class with a physical cone. All right, so it's going to be a triangle if it goes through the tip straight down, and it's going to be an oval if it's going this way, okay, at an angle. If you take a pyramid and you cut it, you're going to get a cross section that's a rectangle if the base is a rectangle. If it's not a rectangular base and it's a square base, then you're going to get a square. If it was a pentagon on the bottom, every cross section that went horizontal would be another pentagon, getting smaller as they go up. So describe each cross section on a cylinder. So we have this to fill in our ISM. If you cut a cylinder horizontally, you're going to get I got the shape right here. Yeah, it's going to be always a circle. Okay. This is what we're looking at. Let me grab a highlighter. Looking at what shape am I getting here? Now it looks kind of like oval there, but understand that they're showing it 3D on the paper, and you would actually be cutting this. So it's going to be round, okay? If I go vertically, I'm going to chop it like that. And then what I'm going to cut out is this. Yes, so what you're going to be getting is, again, just one little piece where my fingers are, then across the top, so it's going to be a rectangle. Oops, better get a pen. Right? Now, if you go through a top diagonally to the other corners, visualize that shape. So if you're coming through a box and you go from here down to there, you're actually going to be getting the shape of a rect. You know, it's not a triangle because you see how this is equal? It's a rectangle. Okay, I wanted to mention one other thing before we go on because it's in the assignment. We're then going to go to the packet. I'm not sure why it's in this packet, but I want to ask you a question. If I took a vertical line and I put a rectangle right there, and I said, what shape would you get if you spun that all around that line? If you took it and you could take this, say it was like movable. This was on a hinge, this rectangle, and you could spin it. Yeah, you'd be spinning it around, right? So it would go like this. And yes, Amato, you would get a, oh, I didn't mean to make it look. It is a cylinder. If you spin a rectangle, you're going to get a cylinder. Now, think about this. A cylinder. Oh, I don't know what I wrote. A cylind. A cylind. I've made a new thing. Do not know where I was thinking ahead of where I was going. A cylinder. If I were to spin a triangle around that line. Good job. Good visualization if you saw a cone coming out of that. That would make a cone. Oh, what would I get if I spun a half a circle around there? No, you would get a sphere. Oh, stop it. You would get a sphere. Oh my goodness, I don't even want. All right, please pull up. I'm going to get the your packet now. Oops, I don't like that one. I want what it's not written on. All right, so in your packet, and we will get through the examples. Oh, I did. I was I don't know why that says all that on there. I think I had a key of it. No, I think I pulled up the wrong one again because it's got, oh, I filled up the one with the key. I made a key for people if they wanted to look at it. So let me get the one that's blank. Doesn't matter. Okay, got some pictures on your paper for you. We already went through these. What you have is two blanks there, and it's edges and vertices. Where the faces intersect are called the edges, and the point where the three or more edges meet is called a vertex, or vertices is plural. Okay. These are already filled in, I believe, right? Okay. I do have some links I could go to if we have time, but right now I would like to get through so you can prepare to do some of your assignment. We got pyramids, cylinders, cones, spheres, prisms. This is a triangular prism. It is named by the triangle base. This is a square prism named by the square base. This is a rectangular prism because all of its faces are rectangles. This one's a pentagonal prism because its base is a pentagon, hexagonal, octagonal, etc. These are the same figures except in pyramid form. Triangular pyramid, square pyramid, rectangular pyramid named by its base, pentagonal pyramid named by its pentagon base, hexagonal, octagonal. Okay, and then they're pointy. Euler came up with a formula that said if you know the number of faces, or well, that the number of faces plus the number of vertices is equal to the number of edges plus 2. It's always that. It's some constant, and I don't believe we're going to have this on our final, but we're going to just look at one example of this. Find the number of edges of a polyhedron with 6 faces, and I believe your paper says 8 vertices. Guys, it says 8, right? I don't know where my 8 went. Okay, so that would mean that you have a 6 for your F. You have a V of 8, and then you're just going to pop them in the formula, and we're going to figure out the number of edges. So 6 plus 8 is equal to E plus 2. 6 plus 8 is 14. And now how many edges would it have? We would subtract 2, and we'd find out it has 12 edges. Okay. Determine whether each solid is a polyhedron, then identify the solid. If it is a polyhedron, name the faces, edges, and vertices. I am not going to have you write down the number of edges for this one. We will count them. I'm going to count the edges for number 1, and then I want you to do all the faces and vertices we'll do for number 4. Number 1, is it a polyhedron? That's what we're determining first. Michael? Yes. Okay, this is a polyhedron. Okay, here's the point, guys. Is number 2 a polyhedron? No, it's a curved, it has a curved surface. Okay, so that's what we're just trying to identify. Yes, it's a polyhedron. It is a pentagonal. We're supposed to identify what it is. Pentagonal prism. It is a prism because it's not a pyramid. Well, actually, it's a prism because it has 2 pentagon bases. It says to name the faces, edges, and vertices. I am not going to name all of these faces on this one. I would like you to do it on number 4, though. So for number 1, we'll just count how many faces it has. Okay, it's got a front, a back, that's 2, and then it's got 1, 2, 3, 4, 5 rectangles. Follow me? 5 rectangles and 2 bases of pentagons would be 7 faces. Number of edges, we would have 5 on the front, all those segments, 5 on the back. So I'm at 10 already. And then we're going to have 1, 2, 3, 4, 5 going around. So we got 5 plus 5 plus 5, which is 15 edges. And then the number of vertices. How many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, number 2 is not a polyhedron, so we don't name them. It is a cone. It's not a polyhedron, it is a cone. We do not have to name the faces and edges. I could tell you what it looks like opened up. Okay. I can't resist. So it looks like. Oh, wait a minute. Or is it upside down? I might have had it upside down. I think I had it upside down. A sphere. It's not a polyhedron. No, it's a sphere. As basketball is an example of a sphere. Okay, and 4 is a yes. It is a triangular prism, yes. So well, if we were to name them, okay, let's just do the number of faces. Okay, why not? You guys could tell me how many, you could give me names for them, couldn't you? Like triangle ABC, and there are 1, 2, 3, 4, 5 faces. The number of, okay, do the edges next. 3, 3 on the back, 4, 5, 6, wait, 9, isn't it? And vertices, there would be 1, 2, 3, 4, 5, 6. All right, and you know that the faces are triangles and rectangles, and the edges are segments. And that vertices are points. Now we're looking at the cross-section of a solid as a plane. You can think of a cross-section again as a very thin slice of the solid. So what matches up? There are several interesting shapes. Again, this was in our ISN. We found out that cross-sections parallel, if parallel to the base, you get a circle. If it's a cross-section through vertex, and in half, then you get a triangle. If you cut it, well, slanted, okay, that's a good way to say it, maybe, or diagonally, then it's an oval. Then an ellipse is actually the name of it. Now, they didn't bring one up. If you went vertical, and I'll just tell you what it's called. If you went vertically through like here, it would be an arced thing, and it would be half of a hyperbola, or it would be a parabola, actually. On a pyramid, if I cut that thing, then I'm going to get a rectangular cross-section. If I cut a cylinder horizontally, I'm going to get a circle. Oh, here's a picture. You ever seen some shapes when you cut them? When you cut a carrot, you get a circle, right? If you chop a carrot, you get little circles, little cylinders. It's a piece of celery's cross-section. To do a rectangle, you get a square going horizontally, a rectangle going vertically. This one is at the bottom of your paper. All these shapes can be cut from a rectangular pyramid if the cut is made at different angles. Now, if it was made this way, which one is it? Good job, because this is shorter than down here. So here, let me give you a visual coming from the other direction. So say if you were coming from the back was up here, and then you see that piece is down here. The cutout was a trapezoid, and it's an isosceles trapezoid. So that was A. Now, it would have been C if you cut it like that, okay? If you cut, well, through the tip, in and out, you would have gotten D. There's a bunch of different shapes you can get out of a pyramid, a square pyramid. These are just some examples of ways to slice it. And now you have your assignments. You got some time to get started on that. Go ahead and get going, and we'll answer questions hopefully tomorrow.